This video is going to be a little bit different to all the others I do, because we're going to do a whole bunch of retro things but in a disturbingly modern way. But don't worry, it's going to get nerdy and detailed. I guess some things never change. But before we get into all the delightfully nerdy details, I should say this video is sponsored by PCBWay, fine purveyor of printed circuit boards. Yes, the idea is pretty simple. You design a PCB, or pick a PCB from their project library, give them some money, and PCBs come back in the post. To be honest, it's all kind of what you'd expect from a company called PCBWay. They also do the same thing with 3D printing, and CNCing, and also injection molding, which may be the thing that you did not expect from a company called PCBWay. They also seem to sponsor the majority of tech YouTube, which is why you're hearing about them here. Right, so I should probably explain a little bit more of what this video is. So you can either think, oh cool, that interests me, I'm gonna keep watching, or oh god no, this is not for me. Now this video is kind of a little bit of a peek behind the curtain a little bit, in that a bunch of the stuff I'm gonna set up is stuff I'm going to use for the channel and future videos, but also in the production of videos as well. Now, I figured this might be of interest to a whole bunch of you, because you might want some of the retro things that I'm going to set up for me, yourself. And even if you don't run these bits yourself, you might be interested in how this is all plumbed together, because some of you is going to feel this is quite a complicated way of doing stuff, but I'm choosing this route because in the long term, this thing's a lot less maintenance to keep up to date and working than other ways you might do it. Because I'm going to build a bunch of stuff using Kubernetes. The last time I touched on Kubernetes, a whole bunch of you in the comments were of the opinion that Kubernetes was just too complicated for you, and that you'd never have the kind of hardware you need to run Kubernetes. What with the fact that most houses don't have a 19-inch rack in a little cupboard somewhere you can shove servers into? And I feel like last time I talked about it, I maybe did lean into that stereotype a bit too much, as in I built it all with a 2U server in a rack mount. And I'm quite lucky to have the space to put a rack in, a rack, and a 2U servers to shove in it. So this time, I'm going to do it all with the diddiest PC I could find. Just to show you don't need some monstrously large server of enterprise-type spec. Nope, this teeny tiny mini PC that's been on the screen for a while, that is more than good enough to run Kubernetes. At least on a home scale. I mean, we're probably not going to use this in production for a large enterprise system. Now, I'm going to try and show that this is all feasible in a home environment where you don't even have a lot of space. Although I probably should mention, thanks to the extremely hot weather we've had in the UK for the last couple of months, the 2U enterprise rack mount thing, yeah, that's been switched off because it generates quite a lot of heat, and that's a pretty small cupboard that it lives in with little ventilation and no cooling. So that's part of why I'm going down the little computer, because little computer doesn't make anywhere near the amount of heat that the big computer does. So I decided to get myself a little Geekom A6, which is a relatively cheap, basically 400 to 500 quid little mini PC, depending on which spec you go for, that will have more than enough performance for the sort of thing I'm going to run on it, whilst not putting out the price range of most people who'd think about doing this sort of thing. Although I should say, obviously this is a lot more than, say, a Raspberry Pi. Now, I was about to click the buy button on this thing when I got a very fortuitous email. Yes, it seems I'm in danger of turning into a proper YouTuber, because I got an email from Geekom who wanted me to review one of their machines. Now, that's not really something I do, so no, I'm not going to review one of their machines. Because I don't really review hardware, and I'm not suddenly going to start just because someone wants to pay me to do it. However, I did decide I would try and be a little bit cheeky. After all, they messaged me. So I told them what I was planning on doing for the video and asked them if they wanted to donate a machine to the cause, and yeah, they did. Yeah, no, really, they did. Surprised the hell out of me too. So, I should point out, I did not pay for the machine I was planning on buying anyway. But I feel like that's a thing you should know when you hear me talking about this machine. I don't think it's going to impact in any way what I say, but yeah, I feel like you should know. And this is also why you can see me unboxing something like I'm a proper YouTuber. Yeah, because normally my things don't come in boxes. Well, not the original boxes anyway. And I must admit, it's quite nicely presented for what it all is. And the packaging was pretty easy to recycle. No packing peanuts. Gotta love no packing peanuts. Have I ever mentioned how much I hate packing peanuts? Anyway, having finally got it all out of the box and plugged it in, I discovered it had Windows 11 installed on it. Now obviously that's going to be of absolutely zero use to me, but I was intrigued to see, was the Windows 11 install process as bad as everyone says it is? And yeah, no, it sucks. I powered the machine up, it already apparently had the operating system on it, just wanted to do some updates. And 1.5 short hours later, it had installed the update. Now in case you're thinking I have have a dial-up internet connection? Nope. Now, I get somewhere between 700 to 800 megabits via my internet connection, so yeah. Anyway, once it had taken a interminable amount of time to install its OS update, it then asked me to log into the Microsoft account I do not have and could not be asked creating. And apparently there was no way to just skip round that easily and just use the operating system, so I surrendered and put Rocky 9 on it, because that's what I was going to stick on operating system wise anyway to run Kubernetes on top of. In case you're interested, that whole install process, including downloading the entire operating system, all the updates, and getting it fully booted into the OS so I could log in, 22 minutes. Yep, 22 minutes to install the entire operating system and all the applications I wanted on top of it, and do all the updates, etc., versus 1.5 hours for an already apparently installed operating system to download some updates. Oh, and one thing I really should mention about this machine, because it's one of the few things they asked me to say in the video, this will soon be available in pink. Yes, like the lady cassette version, it's the same machine, but in pink. I warn them this is a thing I might slightly take the piss out of. However, unlike the lady cassette version, this isn't the why aren't girls using consoles, oh, it's because they're not pink kind of thinking, and then chip it with a game called Milky Princess. No, this is just that some people happen to like things that are pink, we could make it pink kind of decision. Which actually I'm fine with. If you like pink, buy pink things. If you like a sort of greyish metal colour, buy greyish metal colours. I have no problems with them catering to tastes that are not mine. However, the lazy thinking behind the Super Cassette Vision Ladies Edition, yeah, that I was less enamoured with. Although if you do have that version of the Super Cassette Vision, that's now the rare one. To be honest, I think I could have told him in advance that that one was always going to be the rare one. Right, let me give you the hardware specs for this thing, because I was planning on doing that anyway. At the heart of it is an AMD APU, which is a CPU and GPU all in the same package. And this has a couple of advantages. Firstly, it's a pretty small and compact package, which if you're going to put it in a pretty small and compact box, it's a pretty handy thing. And that last sentence will give my pop filter a really good workout. Now, these APUs are quite handy for this class of very small PC, because firstly, it's small itself, and secondly, being aimed more towards the mobile device markets, the power draw on these things is not that high compared to the discrete CPU and GPU. And that's all going to help with keeping this machine cool and being able to run in just, a flat or any random environment you happen to deploy it into. Now, the particular model of the chip they shove in it is a Ryzen 6800H. So that thing's got 2 threads per core and 8 cores in total. So Linux from a scheduling point of view will kind of treat that like it's 16 cores, or at least that's what top will show you. It's got 32 gig of RAM, but because it's one of these APU things, some of that 32 gig of memory is going to be used as memory for your graphics card. So in my case, I've set aside 5 gig of memory for the GPU, so the machine sees 27 gig of conventional memory. GPU-wise, it's a 680M, which has got 12 compute units, which works out as 786 shaders, which, for someone who's just going to use this to transcode video, I am definitely not going to be running Doom in 4K on this. To say that's a lot of GPU would be a massive understatement. I am super not going to utilise all the GPU performance of this machine. And even if you were a gamer and you had Windows installed on this and you were, trying to hammer the GPU, it'd actually be a pretty reasonable spec. Not, 4K 60 frames a second, every detail option switched on good, but 4K, quite a lot of frames and maybe some of the detail levels turned down. In terms of other features of the machine, it comes with a 1TB NVMe stick. Now, there is a second slot in here so you can add another NVMe, but it's a SATA-only affair, unfortunately, and also only takes the shorter sticks. You can also in theory upgrade this thing to 64 gig of memory, but you do have to remove the 32 that it ships with, because there's only 2 SODIMM sockets on there, and both are in use to provide the 32. Now, as you can imagine, with a machine this small, there's not a lot of room to put upgrades inside it, by which I mean there is no room inside it to put upgrades. Luckily, USB is relatively quick these days, and on the back you've got one USB 3.2 port, and there's 2 of them on the front, and there's an additional Type-C USB 3.2 port, as well as a USB 4 port. You've also got one USB 2 port as well, so you've got somewhere to plug in your keyboard and mouse. There's also an SD card slot in the side if you happen to have an SD card you want to shove in it. Networking wise, it's got Wi-Fi 6, and more importantly from my point of view, 2.5 gig Ethernet. In fact, this is the machine that finally persuaded me to get a 2.5 gig Ethernet switch to install at home, so I could take full advantage of this thing and also replace my wireless access points with something that go a bit faster than 1 gig. In terms of other ports, you've got 2 HDMI outputs and also a headphone jack for audio. See, Apple people do like headphone jacks still. It also has quite up-to-date Bluetooth with Bluetooth 5.2, a thing I am probably, to be honest, really not going to use with this machine. Now, I suppose I probably should say, why Kubernetes? Because a whole bunch of you are probably screaming at the screen. Use virtual machines. I use virtual machines. Virtual machines are very good. And virtual machines are actually a perfectly cromulent solution to a certain set of problems. It's just, they're not the problems I've got with this. See, VMs are great if you want a whole virtual machine. Are you going to run a different operating system than the thing you're running it all on top of? And in fact, at one point through this video, that is the thing I am going to do. Yes, we will create a virtual machine on top of Kubernetes. But mostly what I'm going to do is run Linux stuff on a Linux machine, and I do not need the overhead of there being a VM. I want isolation between those things, and that's what containers provides, and Kubernetes is just a way of gluing up networking and disk to containers and getting the containers started and managing them. Now, the reason why a container is better than a VM for doing that kind of stuff is a VM comes with a certain amount of overhead, as you're not just running one kernel here, running all the loads. What you've got is one kernel for the hypervisor, and then every VM is running a kernel. It's also running systemd and logging, and a whole bunch of things that's not the one thing you want that VM to do. So you pay for a lot of overhead making a machine be a VM. It takes a lot of superfluous CPU and RAM to run all the bits that are not the one little bit of workload you actually created the VM to run. With a container, all of them are sharing the same kernel, the same memory, so there isn't a massive amount of overhead for running the container compared to just running that application on your Linux machine. But we do get all the isolation. We also get container images pre-built with a lot of the things we want to do set up in them, ready to go. And we do have even more automation in Kubernetes in the form of Helm, which I'll come to later. But that means to set up some of the services I want to set up, the majority of the work has been done for me, and I can just reuse that work. So that means getting this all set up, and importantly, keeping it maintained is a lot lower overhead, because I don't have a pile of virtual machines to maintain, handling software updates on all of them, etc. What I've got is a series of Helm charts with some version numbers stored in them that occasionally I have to increment, and everything just sorts itself out. So using containers saves me a ton of resource in terms of compute, RAM, etc. But then using Kubernetes to manage all of that and the things that have been built on top of Kubernetes saves me a load of maintenance and setup time as well. And maintenance time is the thing I really want to save here. I want to use this thing, not spend my entire life keeping it up to date. And I expect a lot of you out there are similar. You want to set something up and then you want to use it. You don't want to spend a big proportion of your life doing maintenance work on this thing. So this is why I'm going for what some people would regard as the complicated way of doing something to save me a ton of complexity later down the line. I'm also going to argue, once you know Kubernetes, this stuff is way simpler than doing it the other way, again because the amount of work it saves me in setting stuff up. Right, so let's get into the nerdy details of setting this thing up. Now, you already saw earlier that I installed Rocky 9 on this thing as the base distribution that I'm going to put Kubernetes on top of. And some of you may be wondering, why not do Rocky 10? It's out now. And the answer is because the Kubernetes distribution I'm going to use is not all fully signed off yet on Rocky 10, or at least at the time of recording this. By the time this video comes out, it may well have got there. But as I'm going to get updates to Rocky 9 for the best part of the next 10 years, I'm not overly worried about it being like one version behind at this point. At some point, I'll stick another node in the cluster that's based on Rocky 10, remove this node, reinstall it and shove it back in. So the first thing I do, weirdly, is run an Ansible playbook against this thing. Now, this playbook just contains essentially my personal preferences for how a machine should be set up. So it just goes and installs a bunch of software I expect to be there, sets up a few things I personally find handy, but none of this is essential to setting up Kubernetes. The only reason I mention it is you might see things in this video that are non-standard Rocky 9 and wonder how they got there, and you might wonder why I didn't cover setting that stuff up. Well, it's this Ansible playbook that does any of that stuff that you see. The only thing it does relevant to Kubernetes is it does increase the maximum number of file watches the kernel allows to happen, because this is something Kubernetes uses a lot of. So if you don't increase that limit, stuff will randomly break. So hence me mentioning it here, and it's the playbook that changes that value. And it just pokes the following value I've stuck on screen into the kernel. How you do this, whether you use Ansible or some other mechanism, just as long as sysctl shoves stores that value into the kernel at boot, all will be good. And with that having completed, we now install our Kubernetes distribution on it, and we're going to use K3s. Now, this is a pretty good distribution of Kubernetes for the size of system we're going to run. It's not aimed at running massive clusters and is happy enough on a single machine cluster, which is what this one's initially going to be. It's very easy to install. It has this little install script, which I'm complicating just that little bit more by telling it not to install what's known as a CNI, the Container Network Interface. This is the thing that allows various containers running under the Kubernetes environments to talk to each other. I just happen not to want to use the default one they ship it with, and I'm going to use something called Cilium instead. So when I install Kubernetes, I'm telling it not to install its CNI. And that's it, the script has run, Kubernetes is now installed. It has put all the RPMs in there that we need for Rocky 9, and if you wanted to install this on a different distribution, say, Ubuntu or whatever it is that you fancy, well, it's the same script and it installs the packages for that distribution. And, set up systemd and all the other things that need to happen. So we now have our Kubernetes environment installed, but it doesn't have a CNI because we told it not to install one. So now I'm going to install the CNI I want to install. So I download the Cilium command and I tell Cilium to install. And I do tell it some little extra details. I give it the IP range I want it to use internally for pods. So this is the IP range that containers will get allocated an IP address of to have container-to-container conversations with. And the reason I'm giving it this particular range is this is not Cilium's default range, but it is the default range for K3s, and there are a number of things that assume that stuff is in that range. So hence me setting it. Now, we don't have to get all the install options for Cilium right at this point because we are allowed to modify them later on. Cilium has an upgrade command, and you can tell it to upgrade to the same version, but change the parameters it's installed with. We are then going to use a command called Helm to install something called Argo. And this is the last thing we will install by hand on this cluster, as once this is installed, Argo is going to take over doing all the install work from here on out. As Argo essentially, once it's installed, connects up to a Git repository that tells it what applications and Helm charts it needs to install, and it manages that whole process, and it's all managed through committing files to Git. So after this point, we're not going to be really using the command line anymore, and this is what makes the maintenance of this thing so much less of a hassle, as I just have to modify a couple of values in a file and this thing takes care of doing all the donkey work. So Helm has now installed Argo for us. Now, we're not entirely done with Helm charts because Argo does use Helm charts stored in Git. And a Helm chart is just a chunk of Kubernetes configuration done in a template, so you can shove values in it and reuse that Helm chart with multiple clusters, and yet customize slightly how things get installed to the cluster. Now, once Argo's installed, I connect to its little web interface and log in. I can then link it to a Git repository, which I do. That is the last thing we will link it to directly with its config interface, because that's the repository that contains the list of applications for this cluster and tells Argo what to do. Now, this is not my first cluster, so I have a bunch of these files pre-prepared that I've installed on other clusters. So once I've got it linked to a directory on a Git repo, I then just start copying those files in to do a few of the basic things I want this cluster to do. So the first two things I copy in are related to storage. Now, Kubernetes will automatically provision storage and link it to whatever containers I've told it to. And how it does that is with something called a CSI, a container storage interface, which you can think of as a little driver that Kubernetes uses to allocate storage from a particular storage system. And the first one I copy in is this NFS CSI provider. Now, that allows me to link pods up to remote storage that isn't stored in this cluster. And this is great for anything where you want backups or something just not to live on the machine where the workload is running. And I already have set up a little NAS box that's got a little NFS server on it and a share. So I can just copy in this file that sets up the NFS provider and just give it the share that's for this cluster. And as you can see, Argo now suddenly detects that that application's there. It then synchronizes that application into the cluster, which tells it to go use a pre-prepared Helm chart to deal with this NFS provider, and then when we click into the application, we can tell Argo it needs to synchronize that Helm chart with the cluster, and there you go, that's now set up a CSI provider for NFS. We also want one to let us store stuff on local disk, and the option I've gone here for is using LVM, Linux's Logical Volume Manager, and the reason I'm choosing this is at the moment, we're a single node cluster, so we don't need some big clever multi-node file storage thing, we just need to be able to access some disk. Now, on the machine, I've created a logical volume group, for the remainder of the 1 terabyte NVM stick that's installed in this machine. The OS is using a little bit at the beginning, and I've partitioned it so we have a logical volume group on the end of the stick that's going to get used by Kubernetes and Kubernetes alone. And the CSI provider I've chosen to wrap this is something called Topo LVM, which again has a Helm chart to install it, and we just pass it a couple of values telling it the name of the volume group we're going to let it manage. And once again, Argo detects that application, we sync it into the cluster, and then we can tell that Helm chart to run with the values we've given it, and that's Topo now set up and ready to allocate disk space to any containers that come along by making them a logical volume and formatting with a filing system that that container wants. Now that's installed all the bits of Kubernetes that Kubernetes needs to run regular workloads. We are now going to add some workloads. And the first one I'm going to add is something called Prometheus. And the reason I'm sticking that in is because a whole bunch of the other workloads are going to make use of Prometheus. Prometheus is a thing that will essentially gather metrics from other systems, and we'll store them and let you draw pretty graphs of what's going on your machine. And again, I happen to have a little application definition that I've already written, so we just copy that in, Argo detects it, syncs it, and then we sync Prometheus. And now it'll get allocated a little bit of storage by the CSI to store all its values in. And then when we install other software, well, they will have a scrape target that Prometheus will automatically detect and start gathering metrics from it. And the other little bit of plumbing services stuff we're going to put in that other things will use is something called the Postgres operator. This thing will just sit there and wait for people to define a Postgres database that they want. It will then set up all the containers with Postgres to make it fully replicated. So it'll set up the Postgres main server and then set up a number of pods that contain the replicas. It will also set up point-in-time recovery for us as well and all the backup stuff. Basically, so we can have a full enterprise scalable version of Postgres with an incredibly small amount of work. We just say, hey, we want some Postgres, and it builds it for us. If you were doing this with VMs, we'd have to set up one machine to be the main machine, another VM to be a replica, maybe another replica again, so we've got 2. And if we wanted point-in-time recovery, then we'd be setting up a 4th VM that does that. Where with this, we just say we want Postgres, this version, 2 replicas please, point-in-time recovery, and can the point-in-time recovery stick stuff on the local cluster and in this S3 bucket please. And it just builds all of that for us. This is one of the great advantages of Kubernetes. All this stuff has been done for us already, so we don't have to do it by hand every single time. The reality, if I was doing this with VMs, is I would probably just set up one Postgres server and it wouldn't have replication and it wouldn't have point-in-time recovery, because that's quite a lot of work for a home setup. I would like those things, sure, but I'm not going to bury the time in it. But with the operator, I can have all those things, and it maybe takes me less than a minute to get it all set up each time I want it. If I was doing this with VMs, I wouldn't even have got the first VM with an OS installed and booted in the time it took me to set all of this up. Never alone install Postgres and configure that in its most basic setup. Now, that's the last thing I'm going to set up that's providing services to other workloads. Right, it's time to set up some actual retro workloads on this and have some fun. And the first thing I'm going to set up is something called retro assembly. This is an incredibly good set of web-based emulators for running various consoles and a way of managing all the ROMs and pausing games and streaming games and rewinding games and resuming them, etc. You know, so I can be a retro game streaming type bod if I wanted to be, or, you know, just have fun. Now, luckily, someone's already created a Docker container that contains all of this, so the majority of the work on getting this up and running has been done for me already. Yay! It doesn't, however, have a Helm chart, so I'm going to use this to show you how we make a Helm chart and get this thing up and running. Now, the first thing I do is create a separate little Git project for it to hold the Helm chart. And into that directory, I put this chart.yaml file that just defines what the chart is and gives it a name. I then have a little templates directory in which I put the templates of the things that I want Kubernetes to go do. Now, the first thing I do is create something called a deployment. This is the thing that gets Kubernetes to run a workload and defines what are known as the pods. Before we get too carried away with terms, a pod is a number of containers running together like they're on one host. So the containers could do things like both mount in the same directory and share files between each other, for example. However, we just want to run the one container with retro assembly in it, so this pod's just going to have one container. Now, with Helm being a template system, we don't just put everything we want in this deployment farm. We put in a number of the keys we want to configure, but we then use a template variable to set what the value is. That means that when we install this Helm chart, we can specify a bunch of default values, but we can also override them at install time. So, for example, when it comes to the volumes, which is a blob of disk storage, we use a number of variables to define what the properties of that should be. So when we install on one cluster, we can tell it, maybe you're going on LVM. On a different cluster, we could tell you, I want you to install on the big CIF volume. When you're writing a Helm chart, you're not thinking about just installing it in this one cluster, you're thinking about writing it in a way that it could be installed on any cluster and be customized for that particular cluster. Now, I probably will end up shoving this Helm chart in GitHub for anyone who happens to want to install WebAssembly. And I define a bunch of other things in different templates, some of which are concepts that I'll come on to later. I'm not going to cover everything here. Anyway, once this Helm chart is built, we create an application for it that Argo will then sync in, and that causes it to then go use this Helm chart. And there we go, we have WebAssembly up and running. However, we can't just use WebAssembly, just yet anyway, because we haven't told the cluster that we want this to be available to the outside world yet. And whenever you install a workload into Kubernetes, unless you tell the system the outside world needs to talk to it, the outside world isn't going to be allowed to talk to it. And for web stuff, we have something called an ingress. This ingress rule tells your ingress controller how to set up the website, and all web traffic that the Kubernetes cluster deals with all goes through your ingress controller, and then is effectively reverse proxy to all the workloads running inside the cluster. Now this is quite handy because we can configure our ingress controller to do a whole bunch of auto magic stuff. So, for example, you can configure it to talk to something called your cert manager, and that manages any SSL certificates you need. You can link it up to dynamic DNS, so it automatically sets up your network DNS to go with whatever hostname you put in this ingress rule. And one of the things I added to the Helm chart for WebAssembly was a template for the ingress rule, so we can just specify the name of the host we want this thing to run on. And our ingress controller will magically set up all the reverse proxy stuff, sort out a certificate, and make it available on that URL. If you set up DNS integration, it will also update the DNS server to point whatever name you've selected at the IP address that the ingress controller is available on. And this is where we touch on very briefly one of the reasons why I selected Cilium. Ordinarily, a Kubernetes cluster just has an IP address for each node. When it wants to offer service to something outside of the cluster, you have to have something called a load balance service. Now, this load balancer service is what takes traffic in from the outside world and then hands it over to your ingress controller. Now, if you got this thing deployed in the cloud, your load balancer service might be something like Amazon's Global Accelerator, for example. But here on our local home network, we don't have anything like that. So, this is where Cilium steps in with its L2 load balancer, L2 short for layer 2, i.e. Ethernet. So we have to quickly define a little policy for Cilium to tell it which interfaces it's going to use to do this L2 announce stuff on, and also what it is going to announce. So you can see here I've told it it's going to use any interfaces that match the pattern ENO and then a number. I then define a little IP pool that it can use and set that one as the default pool that load balancer service is going to get an IP allocated from. And then as soon as we define a load balancer service, well, that thing gets an IP allocated to it from that pool. And Cilium has a little election between all the nodes to work out which one of them is going to be the one where traffic for that turns up. And then it uses proxy ARP on the selected node using that Ethernet interface I told it could do to pick up traffic for the IP in the range. And there we go, we now have a load balancer service with an IP address that links to the ingress controller that our cluster can serve HTTP or HTTPS traffic over, which means I can now connect to WebAssembly and start uploading some ROMs. As you can see, it's got quite a nice web UI, and we've got support for running Mega Drive games, SNES games, NES games, 2600 various Game Boys, and also anything MAME can run. And with any of these emulators built in, you can just click, it runs the game, and you can pause the game, rewind the game, set up save states. I mean, this would be great for me for capturing footage of various things, and also I'm probably going to end up actually using this more than I use like other things for running retro games, because it's super convenient. I don't have to worry about, did I charge my PlayStation Portable up, or cabling stuff in, etc. All I need is a web browser. It also makes it a lot easier for my kids to have access to this stuff as well. The only niggle I have with it is that for some reason it's labelled the Mega Drive as the Genesis. I have set set the localization settings to be for the UK for this container. I am very tempted to make a patch that fixes this, because as far as I know, there's basically one country in the world called it the Genesis, and everywhere else called it the Mega Drive or Mega Drive-oo, and this is going to bug me more than it probably should. Right, the next thing I'm going to set up on this retro cluster is I'm going to make it a file and print server for BBC micros. Not emulated BBC micros. Oh no, I mean actual BBC micros over an Econet network. Now, if you're not of a certain age and grew up in the UK, I may need to quickly explain what Econet is. Acorn Computers, the people who made the BBC micro, had their own LAN technology called Econet or Econet. I'll let you argue about your preferred pronunciations in the comments. And this was a low-cost LAN technology for 8-bit computers. It did make it into some other non-Acorn machines as well. Now, technically it existed at the same time as early Ethernet. However, early Ethernet cards were horrendously expensive, and then you had to buy something called a transceiver to plug in to said Ethernet card, and that cost as much as the Ethernet card. In fact, just the transceiver alone cost more than an entire BBC micro. So this quickly became in the UK the most widely deployed LAN technology there was, and was in use in schools so BBCs could remotely access files and save files and do print, and all sorts of, LAN networking type things. The same things that most of us would do, only 10 years before most of us did it. And Acorn produced a number of file server solutions for their Econet network. You could have a BBC with a second processor and a hard drive that weighs more than I do. And yep, I do have one of those things. And it's set up and it works. They also made a dedicated file server unit known as the file store, which had an external hard drive. And again, I have one or two of those and they work. A company called SJ Research also made their file store for an Econet network, known as the MDFS, and they had a couple of other models as well, and I have one of those too. And you would think with all those ways of being an Econet file server that I happen to have, why might I want another one that is for some reason running on a Kubernetes cluster? Well, while all these solutions are pretty cool and I regularly do power them up and do stuff with them, I don't want to leave these things on permanently in my house, overnight while I'm sleeping. Because I wouldn't enjoy all the noise from them, I certainly wouldn't enjoy paying for the electricity bill for them, and I don't want to die in a house fire in my sleep. So having a solution that can sit on a Kubernetes cluster, well, not only would it be ridiculously reliable, realistically I'm burning no more electricity keeping this thing running, and I am happy to just leave this stuff on all the time, because I know I won't die. So if I have this stuff up and running, I can just plug a BBC in anytime I want into the Econet network and use the file store. And that convenience will mean that I will use this stuff more, so my individual beebs will get more time in use because this stuff just becomes easier. It's also pretty great for filming if I just want to set stuff up and show stuff to you. Now you all know what this Econet stuff is. You might be thinking, well, there's no Econet port on that machine because it's not, 40 years old. And you're right, but someone designed an Econet interface on a USB port we can plug into modern machines, and Ken was kind enough to assemble this one for me and send it to me, in exchange for money, obviously. So I can now plug this into my Kubernetes node, so we have a working Econet interface, but I'm gonna need some software, and luckily, I'm the sort of person who will write an Econet file and print server in PHP, because I can, and people told me that I couldn't. So I bundled that into a container. I've already updated it so it can use this Piconet interface, which is the USB Econet interface. And those of you who saw me in Cambridge a few years showing this stuff off knows that it works. So I make myself a Helm chart to start this container, map it to some storage, and I add a little ingress rule because there is a little web management interface for this stuff. And I bring the container up, and there we go, we got an Econet file server. Well, not quite. Some of you will have realized that there is a security model protecting these containers that means that they can't just go opening any random device on the server, because if they could, well, it wouldn't really be that secure now, would it? Especially if one of those devices was, say, the hard disk. But Kubernetes has the idea of a device manager. That runs as what is known as a daemon set. Now, a daemon set is a pod that runs on every single node in the cluster, and it's there to replace the Unix concept of a daemon. Now, these daemon set pods can have a bit more privilege than your standard pod, meaning that they can see all the local devices on the machine. This device manager then detects devices and allocates them to the individual pods that request them. Now, the device manager I've chosen is called Archaea, which is apparently the Greek for edge, and I've probably just butchered its pronunciation horrifically. And once again, you'll be unsurprised to learn that we stand that up using a Helm chart, so Archaea is then running. Then we define what's known as an Archaea configuration object. Now these objects are there to tell Archaea what hardware it should detect, because by default it won't actually detect anything until you give it the list of hardware you want, because you don't want to share out every random device on your machine. So here's the one I set up for our Econet interface. Archaea will then pick that configuration object up, and the device manager will scan to see if any devices that match it are plugged into the machine, and there is one. And to reflect that, Archaea goes and creates an instance object. That shows that it's found the hardware it's looking for and tells us a bit about it. Now, in order for a pod to make use of this, we edit the pod's definition a little bit. Now, pods have what's known as a limit that limits the amount of CPU and memory it can take, and it uses that to help schedule it on a given node. But we can also say that it requires a matching piece of hardware. And assuming our cluster has some of that hardware spare, it will allocate that to this pod when it starts. So my pod running the Econet software gets allocated one of these devices, and it shows up as dev TTY AMC0. So it's effectively detected the thing as a modem, because that's basically what this thing is. I mean, it's a serial port with some control sequences used to access data. Now, it doesn't matter how many of these interfaces we have installed on a node, the pod that gets allocated it will always see it as AMC0. So I configure the software to always access that device when running inside a pod. Now, the clever part of this thing is, if we had multiple nodes in this cluster, I could just unplug that USB interface and plug it into another machine, and the pod would suddenly schedule up on that machine because it's the only one with an Econet device. If I had more than one Piconet interface plugged into a node, then my pod would schedule up on any of the nodes that happen to have an Econet interface, which means I can have a surprising amount of redundancy for an Econet file server. Yes, a version that can survive node failures. And now I've got this Econet port up and running and connected to my file server software, I can just then plug that into my Econet network, which in my case is a little board that looks like this with all the Econet sockets on it, and a little Cat5 connector that I can use to plug that through the wiring of the house and put another board on the other end, and that can be a breakout for Econet in that room, which is what I'm now going to do when I have Acorn stuff I'm filming for you in my dining room. My previous solution for this wasn't kind of wide in the right place for this to be really convenient for filming, as that one was connected to my Synology NAS upstairs, and there isn't a direct cabling path from that down to the dining room where I film. So there you have it. What I'm assuming is the world's first and only Econet implementation running inside a Kubernetes cluster. But this is not the only retro networking technology I'm going to set up in this cluster. Now, where I've now got my Acorn sorted, well, I want to start taking care of my DOS PCs, and for that, I'm going to run something called Netware. From the mid-80s through to the mid-90s, Netware was the networking system for PCs. It allowed a DOS, or a Windows 3.1, etc. machine to do remote file and print operations. There was also pretty good support for Apples, as well as Next computers as well. You could even remote boot PCs off a network card using it. And for machines of this era, Netware is kind of the thing I really want to use to network them. But Netware of this era doesn't use IP, it uses something called IPX as the protocol between them. And IPX is something that most things have dumped support for. So modern Linux does not have IPX support. It used to, but they removed it quite a long time ago. I don't even know if there's an IPX protocol handler for Windows anymore. And also, you might have noted that, also as you may or may not be aware, Netware is not a Linux thing. I mean, much later in its life, when Netware had lost most of its commercial viability, they did produce a version of it that ran on top of Linux. However, at the point that it was successful and the version I want to run, well, Netware is its own operating system that ran on top of a PC. It did sort of use DOS a bit as a bootloader, but nothing else. Once the machine's up and running, it's its own kernel, it's its own operating system, it needs its own drivers. So not something that's traditionally suited to running inside a container. We're gonna need a VM. But we got a Kubernetes cluster. Well, this is where I get to introduce something called KubeVirt. KubeVirt is a way of virtualizing machines inside Kubernetes, as the name might suggest. Now, the way KubeVirt works is it works in a very Kubernetes way, in that we have a custom resource definition where we define the virtual machine we want to run. In terms of connecting up disk to the VM, well, it uses the CSI system. It gets allocated like a pod, because a VM in this case becomes a pod. Any network connectivity you need, well, that's done through the CNI. Kubernetes basically has everything you need to be a hypervisor platform, it's just missing one thing, the ability to run VMs, and that's where KubeVirt sets in. The way KubeVirt plumbs things together is for each virtual machine it will start a pod, and inside that it will run the same stuff that other hypervisor platforms run in the form of libvirt and KVM. So this is exactly the same technology that's used by Proxmox, Overt, OpenStack, the stuff most of the big hypervisor platforms use, except for VMware and Microsoft's thingy. Oh, and VirtualBox if that's still going. So it stands that stuff up inside a container, and to things outside the VM, well, they can use it like just any other pod, so you can set up ingress rules that point at it, or load balancer services, etc. However, with Netware using IPX and Linux not supporting IPX, we need to directly give this thing access to the network at layer 2. So the VM can produce its own Ethernet frames and drop them straight onto the network. Cilium is not going to let us do that, but it's alright because you can install a second CNI. So we're going to install something called Multus. Multus is another CNI, but it does do things like VLANs and directed bridging interfaces onto Ethernet networks. And we install that just like we install everything else. We put a little app into Argo that says what Helm chart to go use and sets a few values, and Argo runs, syncs that into the cluster, and then we run the Helm chart via Argo, and that sets up Multus up and running in our cluster. And then we then do exactly the same thing with KubeVirt. We define the little Argo application that says what Helm chart it's going to use in the values, sync that in, and then we sync the Helm chart, and after a brief wait, KubeVirt is all installed. Now, my plan was to install Netware 6.5, the last commercially released version of Netware, as in the network operating system with all its services. This was the last version the Valve put out before they switched to offering services on top of Linux. Now, the reason I selected this one is because it's still the classic Netware operating system. It still supports all my DOS clients and Apple and NEC systems, but it also offers some modern stuff as well. In that, it comes with a web-based service called iFolder that lets you manage files on the server using a web browser, which makes life a lot easier for me taking stuff from modern systems and putting it on the Netware server. It also has NFS, WebDAV, and also FTP. Heck, it even comes bundled with an Apache web server and a copy of PHP. And initially, the install for this went just fine. The installer setup, ran, installed Netware 6.5, happily supporting all the devices that libvirt was emulating. Although I had to use the SCSI support, as KubeVirt does not support the old IDE emulation that libvirt offers, what with it not being the early 2000s. To be honest, that is a bit of a pain for retro workloads like this, but after the install ran fine and set up Netware, things went less fine. Now, as far as I can tell, the install process runs using the Netware 6.5 kernel and driver set, but what it's installing is Netware 6.5 Service Pack 8, and under Service Pack 8, this thing seems to lock up during boot of the operating system. Now, so far, I've not got too far trying to debug what the heck is going on here. Initially, I assumed it was something going on with KubeVirt, so I exported a disk image and fired it up inside another thing that uses libvirt. And yeah, it locks up on boot in that as well. So at the time of making this video, I've really not figured out why this isn't working yet. I have got a copy of Netware 4 running in the cluster, but I didn't install that in KubeVirt. I used something called Forklift that moved it from an existing hypervisor platform I had to KubeVirt. So it'll kind of do in a pinch, but I really did want Netware 6.5, as I really wanted that bridge between the modern world and the Netware world. Now, you may be pondering, why did I leave this section in if the whole Netware thing didn't work, excluding the Netware 4 thing? And the answer to that is, I think it's nice for you to see the mistakes, the bits that don't work once in a while. If I edited out every single problem there was, you'd just think that all this stuff went really smoothly every single time, and it sometimes doesn't. Trying to get very retro things working in a modern system is, well, it has its difficulties sometimes. Particularly when it comes to virtual machines and drivers and all of that malarkey. If this was just a fairly old version of Linux I was having as the guest operating system that had all the virt.io drivers built in, this thing would just work flawlessly. But it's not. It's its own operating system from the early 2000s. I mean, I had to mess around with the device configuration just to have a working keyboard. At some point when I finally do persuade Netware 6.5 to work, I might well post a little video on it, just so the next person who wants to do this doesn't quite have as hard a road to tread as apparently I'm going to have. So you might be wondering, what retro stuff is he going to run on it next? Well, the answer is, I'm going to get it to be a PDP-11 and run BSD 2.2. Now, this, fortunately, is not going to take a VM approach because we can't be a virtual PDP-11, but there is a very useful emulator called SimH. that does run under Linux can pretend to be a PDP-11, and we can give it a disk image for BSD too. Now, I was thinking I was going to have to build that Docker container with all that stuff in, but no, someone's already done it. Yes, someone called Jay Gorson, and I'm really sorry if I've just butchered your name, has created a very handy little Docker container called Vintage Computing. Some very apt naming there that essentially contains Immich and allows you to bring up a number of DEC operating systems, and it'll let you pretend to be a PDP-11, a PDP-10, etc. And he's wrapped all of that up with all the different operating systems that were available for those machines. So again, I can make myself a little Helm chart that uses that container, assign some disks to it, etc., and lets me bring up and permanently run a BSD box. And also tops 10 on a PDP-10 or ITS or whatever I happen to fancy. Now, I am going to have to tinker with this a little bit, as this container kind of assumes it's just connected up to your terminal and just throws stuff out to standard out. And I'm going to wrap this as a pod, and I'm going to set up a service around this pod that lets you telnet into the emulated operating system that Immich is running inside the container. So this means I can only really handle guest operating systems that have an IP stack and support telnet. But that's alright, because it turns out all the ones I want to run actually do, and Immich lets you configure all that stuff up so you can get IP access into the emulated operating system. Now, I'm not going to go into the details of that for every single one of these images I am going to fire up, because I have a feeling this video is going to be long enough and you probably don't want all of that. If any of you do, say something in the comments and I'll post in a more detailed description of how I've got this working for whichever guest operating system you've asked about. Although I should say that answer will probably be long and detailed and I may not reply instantaneously, just because of the amount of time it's going to take me to get everything together to put that reply together for you. Although now, having said that, if you are putting this together yourself, don't assume that what I've just said means I'm offering to do tech support for you. I am not going to help fix or debug your version of it. I mean, I have a day job and not enough free time as it stands. I also have some things that I'm going to set up on this that are not, strictly speaking, retro, but they are very useful for someone running a retro channel. The first thing I'm going to do is set up something called Minio. Now, conveniently, that already has a pre-built Helm chart, so I have very little I actually need to do here, apart from choose, which storage I want it to glue up to. Now, Minio is something that pretends to be Amazon S3, which is Amazon's cloud-based storage solution for putting blobs of data on their server. And the reason I want to emulate that is pretty much every bit of network backup software that exists supports S3 as a target, including the stuff that I currently run on my NAS. Now, at the moment, my NAS backs up to remote cloud storage for all the important but relatively small files that live on there. For the huge quantity of video I amass making these videos for you, well, that would cost me maybe a little too much in storage, but I do want a regular backup of it. So what I'm going to do is I'm going to get my NAS to back up to this Kubernetes cluster, hitting this Minio S3 service. Now, as I said before, this little machine has got a 1TB NVMe stick in it, which is a lot for doing the sorts of things I'm going to do with this machine, but not if I'm going to back up my entire video content to it. So I have bought myself a regular spinning glass hard drive. Yes, I'm going to back my data up onto Rust. Now, this thing is sold as a 16TB hard drive, which should do the job quite nicely. In reality, it's 14-point-something terabytes because, this whole decimal scam hard drive manufacturers have been trying to legitimize for the last 20 years. But luckily, 14 and a bit terabytes is more than enough for what I'm going to back up to this. Now, you might wonder where I'm going to put a hard drive that is physically larger than the computer it's going to go into. Well, yeah, I'm going to use an external USB drive caddy for that one, and I pick a fairly decent one that's got a little bit of cooling in for the disk and a half-decent power supply, because I am basically going to just leave this running forever. And I stick the disk in, I create a partition on it, and set up a new volume group on it using LVM. And that way I can have a CSI that will only allocate disk space out from this particular volume group, and when I get Argo to install the Helm chart for Minio, I tell it to go use the CSI provider that uses this particular external disk's logical volume group. That way Minio's on the disk that I expect it to be, and when it's allocating other volumes to other pods, well, it's not going to allocate them on this external disk. And this now means I can back up all my video stuff from my NAS to this cluster and the removable hard drive, so I now have regular backups for all my video stuff rather than the irregular backups I had previously. Now I will actually occasionally carry on with the irregular backups because that involved a removable disk that I don't keep in my house. So if the very worst happens, I don't have to rely on the backup that is in the same building as the NAS. And yes, I will probably lose a few video edits, but I won't lose them all. Mostly, this backup is here, the one that's on the Kubernetes cluster, to deal with me having a bit of an oopsie moment. Hello, Future John here. So, between me recording this and editing it together, things have changed a little bit in the world of Minio. The company that owns it is now referring to it as AI Store, and we all know how referencing AI in the title bodes really well for a project. But more importantly, in the open source version they ship, they've gutted the web front end, so they've removed all the configuration tools and other things in there for managing the system, and have replaced it with a simple file browser. Which of course means the web front end got forked. We now have OpenMax.io, which is basically the same as Minio used to be, only open sourced and not a gutted wreck of its former self. So that nice easy Helm chart I mentioned earlier, yeah, I did have to fork that and swap it over to using the OpenMax.io container for the web front end. I dare say a whole new public Helm chart for Max.io will appear at some point, and I won't need to maintain this fork into the future. Anyway, enough of stealing Lee's bits, let's get back to our scheduled programming. The other modern thing I'm going to stick on here is Jellyfin, and that's got a nice easy Helm chart that makes this really easy to install. If you're not familiar with Jellyfin, it's a web-based application for viewing and organising videos, films, TV, that sort of thing. And in my case, I'm going to point it at my NAS so I can use it to view and organise all the random little video clips that I make that go in these videos. They'll give me a fast way of previewing them and organising them. And setting this up is as simple as, again, I create the Argo application that uses the Helm chart to install Jellyfin, and I set a couple of parameters. One of it is the extra volumes parameter that lets me say, hey, see this NFS server over here that's got all my video files on? Yeah, use that. Now this is because I already have all the videos stored on my NAS, and that's where I intend to keep them and put new ones. I don't intend to store that stuff inside the Kubernetes cluster. As for an individual little machine, 1 terabyte is an alright amount of storage, but when it comes to storing your entire video clip archive, yeah, no, it's not that big, and I don't want to store that on the spinning glass disk. I want that exclusively for backups. Now you might think, might this have performance problems? After all, there's probably only 1 gig between that machine and the NAS. And even if there was only 1 gig between these machines, no, that would be fine. It might mean if you're transcoding a whole bunch of videos, yeah, that might take a little bit longer, but mostly you're not. You're just using it to preview and see the stuff that's on there, and it doesn't require more than a gig a second for the Jellyfin container that's running on the cluster to read that stuff off your NAS. However, I should mention, as this little machine's quite modern, it's actually got a 2.5 gig network port, and as I run 10 gig between the switch downstairs where this is going to go and the switch upstairs, and my little Steinology NAS has got 4 Ethernet cables plugging it back into the switch that have been set up with LACP so they can all get used. There is an awful lot of bandwidth between my NAS and this little cluster, at least 2.5 gig, which is rather nice. I am actually getting quite fond of these 2.5 gig Ethernet solutions. I've just bought myself some APs that connect at 2.5 gig, as in theory the wireless standards it supports are faster than 1 gig, so there's not much point in plugging them in at 1 gig if you want more than 1 gig a second over wireless, and actually I do. I'll also mention the other quick little mount point you may have spotted, that of DevDRI. By passing that device to the container, and also letting this container have a few more privileges than normal, it means Jellyfin can make use of the GPU in my machine for transcoding videos, making thumbnails, all that kind of stuff, which means this can live transcode video to anything I happen to be watching previews on. Now, Kubernetes does have a proper solution for giving access to the GPU in a more structured way. However, I'm just opting for this fairly easy mechanism because I have very few things using the GPU on this cluster, and also I don't want to spend another 10 minutes in this video explaining how GPUs are handed around inside Kubernetes. And unless you're planning on doing a whole bunch of AI workloads in here, it's really not worth the effort. Now that's videos dealt with, now I need to set up images, and I'm going to use something called Immich. Immich is a web-based photo manager type thing that kind of looks surprisingly like Instagram, and this will be useful for managing all my photos that I take of various bits of kit, so the little bit of images that get pulled into pretty much every video. Now again, I want the storage for this on my NAS because this is where I've got stuff automatically set up to just dump the photos, but I need a better way of viewing and managing them, which is what Immich is going to do for me. Now unsurprisingly, there is a Helm chart for all of this, so I create the Argo application to use that Helm chart. But this one is a little bit more complicated because it has a Postgres backend. So I also shove into the app, or app set, a little Helm chart that puts an object in there that tells the Postgres operator to set up a Postgres database that Immich can use. Now, that's the nice thing of the difference between an Argo application, which is just one Helm chart, versus an Argo app set, which is a number of Helm charts that get installed to form one overall system. And because earlier we installed the Postgres operator, we don't have to have a Helm chart that builds all of the Postgres database and is all complicated and whatnot. We just put in one database definition and the Postgres operator builds that database for us. It even pops the username and password and all the other login information into a secret that the Immich Helm chart can actually consume. So you just tell Immich the name of the secret and it gets the username, password and the location of the database, etc. all out of that secret. That means we don't need to set any of that stuff up manually, and it's all beautifully secure. And I'm not storing usernames and passwords in my Git repo, because from a security point of view, that's an incredibly bad idea. Now, when Argo rolls this out, you can see it's a proper monster, because in here we actually have 3 Helm charts. We have the Immich one, and all the stuff that it builds, with all its services, ingresses, etc. And we also have a number of database instances, and also a whole bunch of Redis instances as well. Now, I do have to fudge some of the placement rules a tiny bit, because by default, the Postgres operator does not want to put multiple copies of the same database on the same node, because if you're a multi-node cluster, it's better if they're across different nodes. Because if a node fails, well, it can just switch over whichever one of the replicas happens to be master and everything keeps running. But we're a single node cluster, so we have to alter some rules to say, yes, you can put them on the same node, and then tell it we just want 2 copies of this, a master and a replica. And the primary reason for doing this is if for some reason the database hiccups, Postgres crashes, or more likely we're upgrading the version of Postgres that we're on, the replica can take over while the master is down and Immich continues to run, and then it swaps over which one is master again and upgrades the replica. So we've built ourselves a single node Kubernetes cluster running on the world's dinkiest little PC that could fit more or less anywhere in our house, or our flat, apartment, or indeed narrowboat for some of you. And I should probably at this point, after having done all this with it, tell you what I think of the machine itself, because I really like it. Apart from being space efficient, it's also very quiet. I have made this poor little box do some, well, horrible things. I mean, it transcoded about 5 years worth of filming material. It's running loads of databases and a whole bunch of other things I haven't even put in this video. And why I've got the CPU extremely busy, or should I say CPU cores, forcing it to switch its fan on, it's still really quiet even with the fan running. Now, compared to the 2U rack mount server I was using that sounds like a jet engine, especially when it's busy, but even when it's not, I can still hear it downstairs. This setup is going to make me a lot happier and also not annoy my family quite so much. And it'd be nice not to have to answer the question, Daddy, what's that noise? Now, some of you may be thinking, oh my god, but what if you happen to want to upgrade it? You might need more processor or a better GPU or more RAM, etc, etc. To which I'd say, it's a cluster. You can always add another node. And amazingly, Geekon was up for sending me a second node so I could show you that. Here's the second node. Now, adding the node to the cluster is as simple as stick a base operating system on the machine, so Rocky 9 again, and then you run this one command that joins your new node to the cluster. And here's the node showing up in Kubernetes, and suddenly a whole bunch of pods is firing up on this thing. And it is more or less as simple as that. I now have twice the memory, twice the processing power, twice the GPU, because they're 2 identical machines. Oh, and twice the storage. There is, however, one wrinkle in this. When I started this video, I did not intend to show me adding a second node, and I certainly didn't think that Geekon were going to give me one. So, you may remember when I was talking about the container storage interface, the thing that lets you glue up disk to pods, I said this. At the moment, we're a single node cluster, so we don't need some big clever multi-node file storage thing, we just need to be able to access some disk. Yeah, so pods that are tied to storage provided by that CSI, that can't move to another node because the disk storage is on a given node and it can only access it on that node. However, that's not as big a problem as you think it might be, because in my case, half the stuff is coming via NFS from my NAS, so it's not stored in the cluster at all. So, pods that are using NFS can happily migrate between one node or the other node. A lot of the other significant storage use on this single node cluster, there's now a 2-node cluster, is the Postgres databases, and in those cases I can just scale them down to 1, delete the little bit of config that lets it stick more than one replica on a single node, roll that out via Argo, and then I edit the definition again and tell it can have 2 replicas, and roll that out, at which point it instantly makes a replica on the second node. Now if I happen to lose the first node, which annoyingly I called localhost, yeah, again that was another mistake, I wasn't planning on having a second node. The replica on node 2 will be promoted to being the primary, and all my queries will get handled by the copy that's running on node 2 now and using the storage that's built into node 2. Now, what I will do is add another CSI to this cluster at some point that does replicated storage between all the nodes, and there are a number of those I could use. For example, Linstore produces one that uses LVM on each of the nodes and uses its DRDB to replicate the data between those LVM volumes. A persistent volume can only be accessed at one node at a time, but that's fine, it means you can lose nodes and there's a copy of the data on the other nodes and the pods can come up there. There's CSIs that use Gluster, so you can have a replicated file system between the nodes. There's solutions like Longhorn, which is probably what I'm going to end up using in this mini cluster, that takes over a single disk in the machine, or more, that replicates the storage between all the nodes. This is a little bit more complex than the other two, but it's a lot less complex than the next contender, which is Ceph, which, if I had lots of disks attached to each machine, is the one I'd go for. But in this case, I'd rather keep a smaller memory footprint, and there's a lot of fancy features of Ceph I am not going to use in this particular cluster. I'm not going to have it replicating data to another cluster, for example. On my rack mount servers that have many disks in them, I would absolutely use Ceph. Now, you may be wondering, it is all very well me saying, yeah, no, I'd buy one of these given that I've been given 2 of them for free. And that would be a very valid point. Being lucky enough to be given some of these things might make me look at these things a little bit different if my money's not on the line. So I bought a third one. Yeah, no, I bought this with my actual cash money, and here we have Node 3. It's now a free node cluster, so it's finally slightly bigger than the hard drive I have plugged into one of the nodes. If you want to know the answer to the question, would I buy one? The answer is yes, and I did. Your other question might be, why 3 nodes instead of 2? And the answer here is redundancy. With a third node, I can run 2 nodes to their absolute limit, lose 1 node, and everything is still fine. It's almost as if nothing has happened. And that's either because I've scaled the service so it's running on all 3 nodes, or the services that were running on the dead node very quickly restart up on the other nodes and you barely notice, particularly in a home environment. And this is where I'd say these little mini machines really have the advantage. These are relatively cheap. They're less than £500 a go, and if I spent the £1,500 that's the total value of all these machines and spent it on a 1U rack mount server, I would get nowhere near the power of these 3 nodes. I also wouldn't have the redundancy. The rack mount server would also probably draw more electricity, take up a lot more space, and occasionally impersonate a jet engine. And that's fine if you have the space for enterprise type kit. But most people don't have the space for that, or smaller members of your family who won't get irritated by fan noise. And this mini cluster of mini machines approach gets you an awful lot more bang for your buck. I've got 90 odd gig of usable memory across this thing, 24 actual cores, 3 GPUs, and no partridges in a pear tree. And unlike if I'd just bought myself a big machine that had all those properties, I can turn 1/3 of this thing off, do something with it, completely reinstall its OS, put the thing back in, and it's like nothing happened. To be honest, with the workload it's running now, I could probably take out 2 of the machines, and while it would get a bit sluggish, it would all keep functioning until the second node came back, or the third. Now, some of you who have been long-term viewers of this channel will probably remember I did an episode about bulletin board systems, where I actually made a sort of modern Kubernetes-based wrapper for running a DOS BBS. And some of you may be wondering, am I going to move that to this Kubernetes cluster and finally bring it live? And sadly, the answer is no. Now you might be thinking, is that for technical reasons? Is there something that was wrong with that setup? And the answer is, unfortunately not. No, it's not for a technical reason. It's for a legal reason. We've recently had something called the Internet Safety Act passed here. And while we absolutely did need some legislation in that area to curtail some of the worst things that social media companies etc. are doing, this act unfortunately does relatively little to address that, but it does mean I have to work out if anyone who wants to join my BBS is an adult or not, and doing age verification in a text mode DOS application, that's not happening. Also, I'm not going to pay the API provider for doing age verification, because turns out on my scale that's really not cheap. But also, it would require me to get you to create accounts via a web page, and I was trying to recreate the original BBS experience, being that you could dial up to it with an actual modem. Yes, I had worked out how to get a telephone number routed in, or one of those Wi-Fi modems that does telnet in the background for your retro computer. And sign up via web would kind of ruin that whole vibe I'm going for, but of course it's not the only problem. There's also a bunch of requirements on me to police the contents in there as well, and I really don't have the time for moderating that. And with it not being done for a limited company, the potentially unlimited fines if stuff goes wrong is really not something I'm willing to wear personally. So basically I have mothballed the BBS in a more or less ready to go state, and I'm gonna hope when this stuff gets reviewed towards the end of the year by the select committee that they make some recommendations to scale all this stuff back for really small community sites. If they do, well, I will then move all the Argo applications from the cluster they were running on to this one, and yes, this is where the BBS will then run. So let's all collectively cross our fingers. If you got all the way to the end, I'd like to say thank you very much for watching, especially as this involved, modern stuff. If you happen to enjoy it, there is a little button to indicate that fact that YouTube has provided. If you didn't, well, there is another button, and I guess thank you for the interaction. As ever, the comment section is open below if you want to discuss any of this stuff, and I dare say at least one of you is going to tell me, but you should have still used VMs. If you'd really like to help the channel out, why not press the subscribe button, as it really helps with YouTube bothering to tell people that these videos exist.